Welcome back. Hopefully you've been able to just settle your mind. You're not so worried about all these words and graphs and maths and all of that sort of thing. We can put all of these concepts together and then work really nicely and work well through Newton's second law. So what I've done is to just give you a break from the big words and trying to think of all the maths. We're going to talk about an experiment to do with Newton's second law. So some of you might have been able to do this experiment already. Some of you might be coming up to do the experiment, or perhaps you're just going to read through it in the textbook. Whichever one it is, I want to go through it with you. So follow with me as I read through the experiment. So the first part is the investigative question. It asks, what is the relationship between the resultant force on an object and the acceleration of the object if the mass of the object remains constant? Okay, so let's just see what we've got. We've got resultant force, we've got acceleration, and we've got mass. So we've got the three things from Newton's second law. So those three concepts are there. What are we going to use? First thing we're going to use is a ticker timer and a tape. We're going to use a ticker timer trolley, a trolley track, so somewhere for the trolley to run, string, and mass pieces, something to give this object extra mass. And this is what it's going to look like. Okay, so our mass piece is down the bottom here. The trolley is going to run that way. We've got our ticker timer that's going to be putting the little dots onto the tape for us. That way we're able to do the calculations that we need to for this practical. So let's see how we go about doing it. So the first thing, we set up the apparatus as I've just shown you in the diagram. Then you switch your ticker timer on and you let your trolley move freely. You just take your hand off the trolley and let it roll down the slope. Okay, so you're not pushing it or anything like that, you just let it go, right? Switch the ticker timer off, take the tape off. Now, you take the trolley back up to the top. Okay, so we're going to take the trolley back up to the top of the slope, and this time we're going to add a mass piece. So the first one, there is no mass piece. You just let it slide down the slope with your ticker tape attached. The second time, you put a new piece of ticker tape on, take the trolley up to the top of the slope, and now you put a mass piece with some string down at the front or down at the bottom so that it'll pull it down the slope a lot faster. Okay, and you can do that several times if you want. You can change your mass piece a few times so that you don't just have one. Remember, it's a good idea to repeat the same thing more than once if you're able to, so you can improve your accuracy and so that your values are more reliable. But if you don't have that opportunity, you can only do one per mass piece. Do it anyway so that you can see how the things change. Okay. So once you've repeated changing the mass pieces, you're now going to calculate the acceleration of the trolleys by analyzing the ticker tapes produced. All right? And you use ticker timer, you're going to use the period of the ticker timer, you're going to use the distance between the gaps and the number of dots that there are on the tape. There's a whole lot of different ways in which you can calculate it. Once you've done the experiment though, because we had an investigative question and you would have had a hypothesis, what you expect to have happened, we need to come to a conclusion. And this is the conclusion we come to at the end of this experiment. So I'm going to read it to you. It says the acceleration of the object is directly proportional to the resultant force, provided the mass of the object remains constant. So what does that mean for us? That means that we've proved Newton's second law, which is actually a really cool thing to do in the lab. We don't need this really fancy machinery and go to super duper laboratories. You can do it in your classroom with trolley, ticker tape, few mass pieces, and we can prove what Newton said a couple hundred years ago. We can prove it in our classrooms. I think that's pretty cool. Okay, now we get on to the fun stuff. I know some of you who don't like doing questions are going, oh no, questions are terrible. We're going to go through this slowly so that you know how to do this properly. And so when you're faced with this in your test, this will become easy for you. It's not something you have to worry about or panic about. Go through the method so that it works for you. Okay, so follow with me. First question. A 10 Newton force is used to pull a toy train. which has an engine and another cart attached. The train engine has a mass of 1 kilogram and the cart has a mass of 500 grams. The track is smooth, therefore there is no friction. Okay, that's really good to know. The track is smooth, so there's no friction. So let's have a look at the information that we've got. Firstly, we've got a force of 10 newtons. We've got the mass of the engine, and we've got the mass of the cart. Now remember, in our calculations, mass must always be in kilograms. So what you're going to have to do here is you're going to have to do a conversion. You're going to have to go from grams to kilograms. Okay? Have a look at our cute little picture. I wish I could go on a train like this. This looks like fun. Now comes the interesting part. How do we solve this? We need to calculate the acceleration of the train. Okay, so what I'm going to do, I don't expect you to get an answer yet. I'm going to give you 2 minutes to just think how you're going to solve this problem. How are we going to do 1.1? How are we going to calculate the acceleration of the train? And then 1.2, how are we going to calculate the tension in the link between the train engine and the cart? Okay, so 2 minutes. Don't have to get a full answer. I just want to know how you're going to attack this problem, how you're going to start answering these 2 questions. All right, so 2 minutes to try and answer that with a friend, with a group of you. 2 minutes to go. Let's start now. Time's up. Let's see how you attack this problem. Let's go. So the first one, calculate the acceleration of the train. Now, hopefully, somebody is saying somewhere, if they're not saying it out loud, then hopefully you're all saying it in your head. The first thing we do is draw a diagram. Doesn't matter if it's got anything to do, if they don't ask you to draw a diagram, doesn't matter. Still draw diagrams, draw all the forces acting on the object. It makes things so much simpler when you've just got that simple picture to look at and you can work out where things need to go. So that's how I'm going to start. So even though it says calculate the acceleration of the train, I'm going to draw my diagrams first. So I'm going to do one for the train and then one for the cart. So let's have a look. So for my train, what do I have acting on it? All I need to worry about is all the forces acting in the direction of motion. I don't need to worry about gravity, and I don't need to worry about the normal force. So what I've got here is I've got 10 newtons pulling to the left, and I've got tension to the right. So this is for my train. Then for the little cart, all I've got acting left and right, oh, and I can't draw straight today. All I've got acting left and right is my tension acting to the left, and that is my cart. Okay, so I've got my force diagrams now. Now let's have a look what I can do. My equation that I'm going to use is F net equals ma. But remember, your net force is the sum of all the forces acting. So because I've got two objects, it looks like I'm going to have simultaneous equations. Now, I know you're groaning, going, oh no, it's maths again. Yep, physics enjoys maths, maths enjoys physics, so we've got to learn to love both of them. So let's start with the train. For my train, I'm going to say that F net equals ma. Everybody's happy with that, okay? So my net force is 10, or should I say my applied force is 10, minus my tension is going to give me mass times acceleration, okay? And I can actually substitute in my mass, because the mass of the train they told us was 1, and I'm going to end up with that. I'm going to leave it at that for now. For my cart, again, I'm going to go F net equals ma, and because the only force acting on my cart is tension, I'm going to say force tension equals ma. And if I substitute in the mass, remember, I'm just going to put it up here in a different color. The initial mass was 500 grams. To convert it, we're going to divide by 1,000. So we're going to end up with 0.5 kilograms. So here, I'm going to put in 0.5, and I'm going to multiply it by A. Okay, now that's fine if you look at it, but it's not very tidy. So I'm going to tidy up a little bit, and I'm going to give these numbers. So let me tidy up like this. I'm going to make tension or force tension the subject of our equation here. So that means I'm going to need to move things around a little bit and make this equation 1, and this one can stay as it is. I'm just going to give it the name or a number. I'm going to make it equation 2. What I'm then going to do is I'm going to substitute 1 into 2. You can say add 1 and 2 or substitute 1 and 2. So I'm going to substitute make sure I'm spelling it right, substitute 1 into 2. Okay. I want to make sure you understand why we're substituting 1 into 2. So just stick with me here. We've set our equations so that force tension is the subject of equation 1 and force tension is the subject of equation 2. They are the same force. They're the same tension force. So we're using them as our common factor between the two, and we're therefore going to make our two different diagrams or our two different equations equal to each other because we have a common factor. So that is why we're able to substitute 1 into 2. It's the beauty of simultaneous equations. Let's carry on from where we left off, see where this leads us. So I'm substituting 1 into 2. That means I'm going to write 10 minus A is equal to 0.5A. I want to collect like terms, so I'm going to have 10 is equal to 1 plus 0.5, that should be A, plus 0.5A. So 10 is equal to 1.5A, which is fine if you want to leave it as an equation, but we don't. We need to solve for acceleration. So we're going to go 10 divided by 1.5, and if you double check me on your calculators, you will see that I'm going to get a value of 6.67. But remember, in science, unless there is a unit, our value is meaningless. So our acceleration is 6.67 meters per second per second. You've done a lot of work, some good calculations there. We're going to take another quick break and we'll carry on with this question after that. See you after the break.